Welcome to lecture 44. In this week, we are talking about simplex methods. As of now, we have demonstrated with two examples the working of simplex methods. In today's lecture, we will discuss some special cases of simplex methods. So, we will discuss how to handle minimization problem. As of now, we have talked about maximization problem, but how do you handle minimization problems? We will talk about how the simplex tableaus will indicate when you are going to get an unbounded solution or the presence of alternate solutions. We have seen such cases when you used graphical method of solutions. We will see such special cases in the context of simplex method for solution of linear programming problems. So, the first question we ask is, how do we solve a minimization problem? We have seen two important rules. One is inner product rule, which helps us to determine which non-basic variable will become basic variable. The other important rule is minimum ratio rule, which helps us to determine which basic variable will become non-basic variable. So, how these rules will be changed, whether there will be change or not. If there is a change, what kind of change will there be? There are two approaches to solve a linear programming problem, that is a minimization problem. First approach is straightforward. You can convert the minimization problem to an equivalent maximization problem by multiplying the objective function by -1. So, all you have to do is to convert the minimization problem to an equivalent maximization problem by multiplying the objective function by -1, and then you treat it as maximization problem and follow the steps that we have demonstrated as of now. So, note that the minimize f equal to x1 plus 2 x2 plus x3 becomes maximize minus f, which is minus x1 minus 2 x2 minus x3. Note that there won't be any change in the constants. The second approach is actually about applying the inner product rule for a minimization problem. The coefficient in the Cj bar row give the net change in the value of objective function, that is z, per unit increase in the non-basic variable. That is what we have known as of now, that the coefficients Cj bar give the net change in the value of the objective function per unit increase in the non-basic variable. A negative coefficient in the Cj bar indicates that the corresponding non-basic variable will decrease the value of the objective function. A positive coefficient represents that the corresponding non-basic variable will increase the value of the objective function. If Cj bar equal to 0, it means that the corresponding non-basic variable will not change the value of the objective function. Similarly, a negative value of Cj bar will mean that the corresponding non-basic variable will decrease the value of the objective function. So, thus, while solving a minimization problem, the non-basic variable with most negative Cj bar should be chosen to enter the basis. In case of maximization problem, we have seen that the non-basic variable with most positive Cj bar will enter the basis. So, we can modify this rule appropriately for minimization problem such that the non-basic variable with most negative Cj bar will enter the basis. Note that the minimum ratio rule will remain unchanged, because this rule is related to the feasibility of the variables concerned. The variables has to be greater or equal to 0. So, this condition is maintained when you change the non-basic variable by this minimum ratio rule. So, minimum ratio rule remains unchanged, but the optimality criteria now changes. So, for maximization problem it was all Cj bar less or equal to 0. For minimization problem it will be all Cj bar greater or equal to 0. So, in a simplex W, when all Cj bar greater or equal to 0, it means that there is no other non-basic variable which can be made basic variable and further decrease the value of the objective function. That means, we have reached the local optimal solution. Since the linear programming problem is a convex programming problem, the local optimal solution is also global optimal solution. So, the optimality criteria for minimization problem will be all relative profit coefficient values Cj bar are greater or equal to 0. Next, let us consider unbounded optimum special case. We have discussed the unbounded optimum for linear programming problem when you discuss graphical solution method. A linear programming problem has unbounded optimum when its optimal value is not finite. For maximization problem, the optimum tends to plus infinity, and for minimization problem, the optimum tends to minus infinity. The figure shows that the given linear programming problem has unbounded optimum. This is the line corresponding to the objective function, and you can check that you can go on moving the objective function line and increasing the value of the objective function infinitely. So, there is unbounded optimum. So, how is this indicated in simplex method? In simplex method, unbounded optimum is indicated when the minimum ratio rule fails to identify the basic variable that will leave the basis. In simplex method, unbounded optimum of linear programming problem is indicated when minimum ratio rule fails to identify the basic variable that will leave the basis. Remember the minimum ratio rule? You basically divide bi bar by AIS bar such that AIS is greater than 0 and you take the minimum ratio, and that is the maximum increase in the non-basic variable xs, which will retain feasibility. Suppose we have identified the non-basic variable with most positive reduced or relative profit coefficient Cj bar to enter the basis. Now, we use the minimum ratio rule to decide which basic variable will leave basis. At this stage, the minimum ratio rule may fail if none of the constant coefficient of the non-basic variable selected to enter the basis is positive. So, to find out the minimum ratio, you evaluate bi bar divided by AIS bar. What is AIS bar? AIS bar are the constant coefficients of the non-basic variable selected to enter the basis. So, AIS bar are the constant coefficients for the non-basic variable that has been chosen to enter the basis. Now, if all these constant coefficients are negative, then I cannot evaluate this ratio, because AIS bar has to be greater than 0. So, minimum ratio rule fails when all the constant coefficients of the non-basic variable selected to enter the basis are negative. Consider the tableau shown. The most positive Cj bar is 11 corresponding to non-basic variable x2. Sorry, x1. So, the most positive Cj bar is 11 and this is corresponding to the non-basic variable x1. Now, the constant coefficients in this x1 column are both negative. So, I cannot find this ratio. Minimum ratio cannot be found because AIS is not greater than 0. So, what it means is, if AIS is negative, as we increase the non-basic variable, the values of the basic variables will increase indefinitely without being infeasible. That means, the objective function value can be increased indefinitely. In this particular case, as I increase x 1, both the basic variables x 2 and s 1 can be increased indefinitely without making them infeasible. That means, I can infinitely increase x 1 to make the objective function value larger and larger, because x 2 and x 1 will be increased and they will still remain feasible. So, the linear programming problem has an unbounded optimum. So, an unbounded optimum will be indicated when the minimum ratio rule fails, because the constant coefficients under the non-basic variable that enters as basis are all negative. Next, we talk about another special case, degeneracy and cycling. A basic feasible solution in which one or more of the basic variables are 0 is called a degenerate basic feasible solution. A basic feasible solution in which one or more of the basic variables are 0 is called a degenerate basic feasible solution. A basic feasible solution in which all the basic variables are positive is called non-degenerate. So, in case of degenerate basic feasible solution, there is at least one basic variable whose value is 0. And in case of non-degenerate solutions, all the basic variables are positive. Consider that there is a tie between two rows while applying the minimum ratio rule for a simplex W. This tie can be broken arbitrarily by choosing any of the basic variables to leave the basis. So, when there is a tie between two rows, that means the value of the ratios are same for two rows. So, you can arbitrarily choose any one of these two rows to break the tie. But when a tie happens, at least one basic variable will be 0 in the next iteration, and then in the next iteration we are going to get a degenerate solution. So, once again, if there is a tie between two rows while applying the minimum ratio rule, the tie can be broken arbitrarily by choosing any of the basic variables to leave basis. But when a tie happens, at least one basic variable will be 0 in the next iteration. What it means is that in the next iteration, we will get a degenerate solution. So, what is the problem with degenerate solutions? When we have degenerate basic feasible solution, it is possible that the minimum ratio will be 0. This implies that when a basis change is performed, there will not be any improvement in the value of the objective function. So, when we have a degenerate basic feasible solution, it is possible that the minimum ratio will be 0. This implies that when a basis change is performed, there will not be any improvement in the value of the objective function. Thus, simplex method can go through a series of iterations without making any improvement in the objective function. So, it will be considered as if the simplex has entered a loop and from one iteration to another there is no change in the objective function value. So, simplex method is going through a series of iterations without improving the objective function value. This is known as cycling. Fortunately, cycling may not happen all the time. It does not happen often. Also, a solution may be temporarily degenerate. The example that you see is an example where cycling is possible. So, it is a simple example, but cycling is possible. Now, there is Bland's rule to prevent cycling. This is also known as smallest subscript pivoting rule. If we follow Bland's rule during pivoting, you will be able to prevent cycling. It can be proved that if you follow Bland's rule, your simplex will converge in a finite number of steps. That means, there will be finite number of tableaus and you will reach the optimal solution in finite number of steps. You will not enter in an infinite loop. So, Bland's rule states, among non-basic variables that have a positive relative profit coefficient, choose the one with least index. So, among non-basic variables that have a positive relative profit coefficient, choose the one with least index. Among rows that satisfy the minimum ratio rule, choose the one with least index in case of ties in the ratio test. Among rows that satisfy the minimum ratio rule, choose the one with least index in case of ties in the ratio test. So, basically the Bland's rule to prevent cycling is about choosing smallest subscript during pivoting. Next, let us talk about the case where alternate optimal solution is possible. In case of graphical solution of linear programming problem, we have seen that a linear program will have alternate optimal solution when the objective function is parallel to a constant line. So, when the objective function is parallel to a constant line, the linear program will have alternate optimal solutions. So, the figure shows that the objective function line is parallel to line BC. The feasible solution space, for the linear programming problem is obtained by points O, A, B, C, and it is noted that the objective function line is parallel to the line BC. It means that every point on line BC is an optimal solution. So, you have alternate optimal solution. So, how is this indicated? In simplex W. An alternate optimal solution is indicated when there exists a non-basic variable whose relative profit coefficient is 0 in the optimal W. When all relative profit coefficients for non-basic variables are strictly less than 0, we have a unique optimal solution, but an alternate optimal solution is indicated when there exists a non-basic variable whose relative profit coefficient is 0 in the final optimal W. That is important when we are talking about final optimal W. So, this is an example of final optimal W. Your non-basic variables are S2 and S3. X1, X2 and S1 are basic variable. Now, for the non-basic variable S3, the relative profit coefficient value Cj bar is 0. So, if Cj bar value is 0, it means that if that non-basic variable is made basic variable, there will not be any change in the objective function, because Cj bar represents the net change in the value of the objective function when the non-basic variable is changed. So, if Cj bar for the non-basic variable S3 is 0, it means that if S3 is made basic variable, the objective function value will still be 14. So, it means that there is alternate optimal solution. So, we can make S3 a basic variable, and that will not change the objective function value. Objective function value will still remain 14. So, thus we have alternate optimal solution. So, alternate optimal solution is indicated if Cj bar value in the final optimal W for a non-basic variable is 0. In the given example, Cj bar for S3 is 0. So, if S3 is made basic variable, the objective function value still remains 14, which is optimal value. So, I have alternate optimal solution. Next, let us talk about infeasible solution. Every possible solution violates at least one constraint. Consider points A, B and C. Every possible solution violates at least one constraint. So, what you see is an example of infeasible LPP, infeasible linear programming problem. It does not have any solution. So, a linear programming problem with inconsistent constraints have no feasible solution. A linear programming problem with inconsistent constraints have no feasible solution. This situation can never occur if all the constraints are less or equality type and the right hand side constraints are non-negative, because in such cases we have already seen that introduction of slack variables always provides a basic feasible solution. For other type of constants, we will use artificial variables to get initial basic feasible solution. How to use artificial variables to get initial basic feasible solution we will learn in the next class. But to get a solution, the linear programming problem must have a feasible space. So, a linear programming problem with inconsistent constants will have no feasible space and thus no feasible solution. With this, we will stop lecture 44 here.